My name is Eric. I'm from the National University of Singapore, and Radha here is my ex-colleague. I just recently joined NUS as a lecturer in analytics and artificial intelligence. Earlier on, I had about coming to 15 years of experience in both the financial sector and in we would call it the data science sector, if you like. So, am I a data science guy or a finance guy? I would say that maybe I'm a finance guy who knows data science. Thank you. And coming to that, I will let my colleague introduce himself, Radha.
Yeah, hi, I'm Radha. I work at Reuters as a data scientist. I've been in the financial domain for about close to 12 years. Earlier, my transition into this space has been from trading. I was essentially a trader, and then at Goldman Sachs, and then I moved into data science, and now I'm at Reuters. We essentially, as the talk progresses, you will realize that we have done some work in the area of graph. Since by nature it's a commercial enterprise that we are working, so our applications, our research output has to be more real life in terms of revenue generation, to be honest with you. So I think you will see that Eric's talk would typically talk about many concepts, and my little demonstration towards the end would actually highlight what we can do to actually take these concepts and actually create a revenue generating app, so to say. So with that, I'll allow Eric to speak.
Thanks, Radha, again. Yeah. And thanks once again to the audience for coming to attend our talk. Now, today, the topic of our presentation is on graphical analytics, 3 C's and practical applications. Okay. Our agenda is that, firstly, a very short introduction on graphical database. I assume that most of you will know, but just for completeness sake, I'll just go through what's a graphical database and why is it becoming more popular nowadays. The second subject, I'll touch on the 3 C's. You know, in big data, you have 3 V's, and I'm just calling the term 3 C's here to make things easy to remember. After that, we will talk about some practical applications of graphical analytics. We will talk of its use in financial stability. We also talk about its use in blockchain analytics. And lastly, in supply chain analytics as well. And then my colleague will actually give a demonstration of some of the work they've done in Thomson Reuters, of some real-world applications. And we conclude. Thank you. Introduction to graph databases. Now, this is just one slide. The point okay. Graphical databases has become very popular nowadays, as we all know. You know, it's ubiquitous, it's common. All the big boys in tech, Google, Facebook, are all using graphical databases as a form of storage for them. Okay? It's of course the performance is much faster than SQL and even other non-relational databases. It's index-free and benefits a lot of traverses performance. Okay, and for example, Facebook, they have a social graph, which is essentially a graph of all the connections that you have, the friends of friends, and in the social context. Google Knowledge Graph, which came out, I think, about 2-3 years ago. That also essentially is for a recommendation engine based on related concepts, related entities. That is a graph itself. Okay. And we have as well, Thomson Reuters, we have the big open link data, my ex-company, and where Radha is working as well. We have an initiative called BOLD, Big Open Link Data, which is essentially a graph of everything you can conceivably think of. Graph of entities, organizations, people, which Strata will espouse more on, and even on events. Now, you can think of graph as a very natural feed for big data. You see, it's a very natural feed for a data lake. We have data of all types, all formats, structured and unstructured. You put everything into the data lake. And so a data lake has a graphical database. So, and what's the next step after that? The next step is to glean useful insights from your database, from the graphical data. And that's where we have graphical analytics, the 3 C's of graphical analytics. See? Now, when I was studying graphical analytics, I was quite, you would say, I was quite a newbie at the time. I was quite confused. There's a lot of tags and a lot of material on graphical analytics. And I tried to find a common theme among them. I find that it can be divided into 3 C's. What are the 3 C's here? The first C is centrality. The second one is clusterness and connectedness. Now, these 3 C's provide a framework of thought of how you want to analyze your graph. See, any algorithm can fall under these 3 C's. The first one, centrality. You ask a question, it's like how important a node is. A node is, of course, is an element in the graph. Okay. Clusterness, the themes, in a big graph, you can see what are emerging themes, what are the central themes, in the whole graph, or in a subgraph. That is the clusterness, obtaining themes from the graphs. The third C is connectedness. It's about the relationships, the relationship between nodes, between a friend and another friend. So the 3 C's form a framework of thought of how you want to extract insights from your graph. And that's essentially what the main topic of our presentation and what we want to share with you. Okay. This is notwithstanding, this is often a challenging first step, but by having a framework of thought, you will help a lot. Okay, what questions do you ask in regards to centrality? You can say, like, which node is the most important, the most influential? Who are the influencers? That will be in the social network context, right? Which node impacts most on the network stability? That will be in the financial network context. Say in the banks, which particular node is heavily influences the network stability, the importance of this particular node in that whole network. That is some questions that you ask regards to centrality. The second one is clusterness. Earlier on I mentioned is about getting common themes in the network. Question to ask is that let's say in the Facebook, how in a graph you can see it's all quite in a very big complicated graph. You can see a lot of networks. It's quite complicated. And how do you want to extract out the groups of friends? How do you identify cliches in the whole network? This is all about cluster. All right. The second one is like is opposite of it. Which nodes lie outside of a cluster? In financial modeling, it's very important to be aware of outliers because outliers are the ones that actually destabilize the whole systems. So, and of course, fraud analytics as well. Now, fraud analytics tends to look at the outliers. Those people who are trying to be something different. It has a knot in a particular cluster, which is the main premise of identifying fraud. The third one is supply hubs in the supply chain analytics. This I'll let my colleague talk about later more. And then which customers in the network share common threats or characteristics? This again is you try and find the common some techniques you use K-means clustering. Which are the common themes in the network. The fourth, the last one for clusterness, of course not the last one per se, but the last on this list is where the risk concentrations in portfolio risk management. In my synopsis, I talk about how graphical analytics can be used for portfolio management. In portfolio management, for guests from a non-financial background, diversification is key. We have the correlation metrics, and we want a well-diversified portfolio so that you don't get you don't get burned per se. So by identifying the risk concentration in a portfolio risk management in the graphical analytics, you're able to kind of supposedly have a free lunch, the only free lunch in finance portfolio risk management. The next C is connectedness. How are nodes linked together? What are the questions that you can ask in the various contexts? What is the influence one node has on another particular node? suppose in a Facebook context, if something happens to a friend A, how would that impact, say, another node? It could be like 1 degree of separation, 2 degree of separations. And here we're all talking about connectedness. And in a news effect cascading from the main node to another, a lot of financial crisis happens because of the propagation of fear, the propagation of news in a social network or through the news media. So, of course, this is a form of, it's an area of active research which I'm interested in doing presently. How do news get cascaded? How do prices get formed? Who are the buyers and sellers? And all this is a form of connectedness in the network. And we have a very popular, the shortest route from one node to another. We have the GCAS algorithm. The traveling salesman. The shortest path. All this is all well studied. I think even a century ago. And then, just not too long ago, I was Googling Google, and up comes some related search entities. I'm sure all of us have the experience. When we Google something, and then Google will show you a lot of related entities. That all comes from the knowledge graph of Google. And how about recommendation engine? Of course, you have collaborative filtering, user-based, content-based. But another area that the networks can be used is also in a recommendation engine. You're finding connectedness, related entities to what you're looking at or interested in. In KYC, know your customer. It's something that we did, Rada and I, in Thomson Reuters. We use a network to identify blacklisted candidates or entities. Nowadays, criminals are smarter than you. Of course, they get smarter as usual. And instead of just knowing that a particular entity is blacklisted, they tend to use related entities. It could be an offshore company that's related to the actual blacklisted company, and even some degree of separations. So by using a network, we are essentially using a net instead of just a fishing rod to identify the blacklisted company or entity. There's some questions that we can ask. I can go on and on, but essentially, the graphical databases, graphical analytics can be grounded into these 3 C's. Centrality, how important a node is. Clusterness, what are teams? What are the recurring themes that you can see in this particular graph? And the third one is connectedness. How is one node or how is one friend or how entity related to another? How would if something happens to one entity, how would it affect some entity that is related to? These are the 3 C's to form a framework of analysis, which I would, yes. So just now I asked the questions, and now I provide the algorithms and measures. Now I wouldn't go too much on each of these algorithms, otherwise it would take a few days. But just to list down some of the algorithms in that particular category. For some of the centrality measures, how important a node is. We have PageRank that actually originated from Larry Page from Google. Identify which are the most important nodes in the network. That is what makes Google. It's a very important algorithm. We have K-means clustering. We have affinity propagation, which is another clusterness algorithm. In fact, we use affinity propagation for our supply chain analytics to identify supply chain hubs. Again, I'll leave that to my colleague. We have a depth-first traverser, a breadth-first or a breadth-first. By depth means that you're going deep inside and try to expand your subgraph. Whereas breadth-first, you try to go on the more horizontal level traversers in the graph in order to identify which are the clusters here. Of course, we have the Markov cluster algorithm, which does a Markov chain simulation of a correlation matrix to eventually identify the clusters. These are some of the algorithms that are in centrality and in clusterness. Connectedness, traveling salesman is probably a century-old algorithm. How you want to, in the network, how do you find the fastest and cheapest way to connect the the various nodes together. For example, if you have a Grab driver, how would you want to deliver your, suppose you have a Food Panda or Uber Eats, how do you want to deliver the food in the fastest and most economical manner? This is something on a network here. GCAS algorithm, and a node degree. We have also epidemiological and word-of-mouth model in network information diffusion, something which I'm doing research on in the financial sector. Yeah. We all know that finance is influenced not only by fundamental factors, it's also influenced by behavioral, how news are being communicated in the network, in the social media. And the word of mouth is definitely one way that information get diffused in a network, the social media network, or it could be in some of the popular media outlets like Seeking Alpha or Trade Heroes, and all these are all very important aspects of how information get diffused in the network. And all this falls under the connectedness algorithm, how you want to frame your analysis. Okay, the next part I will touch on is to some practical application of graphs. I'll touch on two main aspects, financial stability and blockchain, and my colleague will espouse on supply chain. Now, earlier on, we had done some work on using graphical analytics for portfolio risk management, but I decided that it would be more interesting to talk about how graphs are being used in the context of financial stability and in blockchain analytics. Of course, I've also sought the consent of some of the co-workers, of some the people who work on it. Financial stability. Now, just a decade ago, we all know about the Lehman crisis. There was a huge thing. It impacts everybody's life. Everything came to a standstill and then many jobs were lost. Yeah. So at that point, Ben Bernanke, the Federal Reserve Chairman, was talking about too big to fail banks. They want to build up banks. In fact, almost every bank, the bigger banks were all bailed out. There were a lot of backlash at the time, you see. So now the federal funds themselves have come to study this network. Now, what precipitated this particular financial contagion? There's something like a federal funds market, which is essentially an interbank loans market. It's huge. Every day we have in the US about 2,800 loans with a notional of 350 billion a day. You see, if this market doesn't work, if liquidity freezes for any reason, now it's just like an oil in the engine. The engine will stop, and the economic engine would stop, and actually causes the financial crisis partially. There's a major reason behind that, right? And this particular interbank market, interbank loans, is essentially a graft, which is studied by the federal funds at a point in time just after the Lehman crisis. Okay. And the graph here is that the banks are the nodes, and the interbank loans are the edges in the graph. So imagine that you have a big economic system, you have many banks and many nodes, and you form that in the huge network, huge graph, right? This is just showing that the bank benefit was still there. Okay. And coming to that, we asked, there are two main types of graph, distortive and assortative. So what are they? Okay. In a distortive graph, you can essentially see some hubs. You can see spokes and hubs. As you can see over here, this is one hub and a lot of spokes. It's quite distinct. Technically, it means to say that nodes of the same degree tend to be connected to nodes of the same degree. All right. For assortative graph instead, it tends to be is the other way around. Nodes of the same degree tend to be connected with nodes of, say, a different degree. See, so there are no hubs per se. It's quite messy. Assortative is quite, you can call it a homogeneous or something. My question to you is, which graph do you think appear in, say, a social network, and which graph appears in a financial network, and what are the implications for it in, say, for stability? Let's say for assortative, do you think a social network belongs to this? Well, I think it's generally social networks of Facebook tend to be assortative. for financial networks, it tend to be dissociative. Okay, and say supply chain hubs tend to be dissociative graph. Okay, of course, this goes back to some of the graphical measures, clusterness, back to the 3Cs here. So, this graph here is what you see, a dissociative graph. It's the actual graph that's in the federal funds market here. It shows that this is, for example, could be a too big to fail bank here. In this dissociative market, you have a node, a bank, which lends money to, I think it's an intermediary, which lends money to a lot of smaller counterparties. And this is a too big to fail bank. See? And that's where all the bailout comes, because if this bank fails, a lot of intermediaries will fail, and it will just cascade throughout the whole financial sector, which is what happened in the financial crisis at the time. So a dissociative graph here. Okay. And I think I'll skip this for sure. Yeah. And this article of interest for federal funds market I actually liaised with Morten Beck, and he's consented to share this with all in this data science conference. Okay, the next thing I'll share on will be on the blockchain applications. Now, a few years ago was big data, and then now it's maybe AI, deep learning, and I think we all know that now a lot of people are talking about blockchain. That's why also the reason why I thought that it would be more appealing to some of our guests here. Okay, so firstly, this is on a project Ubin 2, which is by MAS, the Monetary Authority of Singapore, right? And this project Ubin 2 is actually proof of concept for the three main blockchain players, the R3, the Ethereum, and the Hyperledger by IBM. Of course, with the proof of concept, you want to know how would they use blockchain for financial applications in a real world. I mean, what are the benefits that you see out of that? And that's what I would like to talk about. So to reiterate, the project Ubin 2 is a proof of concept for among the blockchain players. So distributed ledger technology is just a technology underlying blockchain. So again, as I mentioned about the federal funds market, there's a similar market among all the banks in any country, in Singapore for definitely, and in all the various countries. All the banks, as we consumers, we borrow and deposit money into banks. The banks themselves, they have active interbank markets. And this active interbank markets forms a graphical network, as we earlier mentioned. So and among themselves, they have to settle, the money that they lend to one another. So, and this DLT, the blockchain, is being used for real-time gross settlement system. See, and essentially, the blockchain is being used to effect liquidity savings mechanism. Now, I will describe more about this in the next few slides. Okay, the one that I was mentioning about is more on R3 Consortium, which is kind of like my institution has a bit of a forthcoming partnership or something. Okay, so a major pain point in this particular network of banks and the loans is a gridlock. Okay, what are gridlocks? A gridlock means to say that, let's say it's a very simple example here. The banks themselves, they have sufficient funds. They are well liquidated. They can meet their own liabilities. But for whatever reasons, because of this whole network, of borrowing and lending to counterparties, they are not able to effect any payment in the network. Let's say, for example, for A has $8. Okay, it owns B $10, but C owns A $8. Logically, A should definitely be liquid. A would actually have a net position of $6, okay? But it's not able to pay B because it's only $8. It cannot effect $10 payment to B right away. So that's a gridlock. See, only if you get some money from C, then you have $16 in order to pay B $10. Okay, but the same thing happens to B, and the same thing happens to C. B can't pay C, and C can't pay A, because it's all a gridlock until they receive payment from the various the other party. So this is essentially a gridlock, and this is a very real thing in a interbank market. So we see this graph, and we use we use graphical analytics to resolve this gridlock. Now, I need to emphasize that the blockchain, as you know, is which is used over here in interbank market, are essentially smart contracts. But we apply graphical analytics on these smart contracts. I mean, the smart contract is essentially the loan between A and B, which is one fragment of the graph, node A and node B, and they have a smart contract, a loan with B. So you can imagine this whole graph has been, these fragments become a whole big graph. Okay, so and all these are smart contracts, part of the blockchain, and you bring all these smart contracts together in a graph, and you apply graphical analytics. You apply graphical analytics in the area of resolving gridlocks, which is essential because if a gridlock happens, there's a liquidity freeze, and the whole again it's like an engine; it just cannot run. And again, and this is an example, which is of a particular, how the graph looks like in the interbank market. Okay, so the graphical analytics you can use is first to detect the closed cycles in the network. Of course, potentially there are many closed cycles in the interbank network. It actually uses the algorithm Roca-Theta. Okay, it's a variant of the breadth first search, which early on is breadth first search. Is one of the variant of it algorithm. So it resolves gridlocks to first identify closed cycles within, or I would say, subgraph in the network. And once it's identified the subgraph, you essentially net off all the liabilities in the particular subgraph. So that, to cite the example over here, this is obvious gridlock. So the subgraph will net out all the positions of ABC. So essentially, you will net up all the positions for ABC, considering the loans. That's what the central bank does as an intermediary. So that effectively, there's no transfer of cash among the different counterparties. And that uses the graphical analytics to first identify all the various subgraphs in the interbank market. And then it netted out all the liquidity, which is what I meant here by a liquidity savings mechanism. And once it's done, not trivial, because we're talking about many nodes and many loans. And once it's done, you can simplify the network, and the whole network can run again. Okay. After this, I'll let my colleague talk about supply chain users, which are some of the work we have done. Thanks, Radha.
Very good afternoon. I always consider Eric as a person who talks a lot about very complicated stuff. I've been from trading. I primarily do stuff. I don't understand most of what Eric does, or whatever he does. I pretty much implement it. That is my kind of work profile. Anyway, so this is a kind of a data conference. So I thought I would explain. I would just take a couple of minutes of your time. One, I have only few slides, and second, I'll show you a demo of what we have done. So since it's a data conference, I just want to highlight one specific aspect of data, which is open data. I'm sure the word open data you've heard in many contexts. But in the context of, let's say, Reuters, I just want to explain this aspect. We have made a massive amount of data set available for public consumption. So the word open data, the semantic of it is very interesting, because what it means is under Creative Commons license, you can just use this data and you don't have to pay anything. So when you look at a lot of open data sets available outside, it's difficult to find data sets on organizations. Like you want to find the hierarchy of organizations, which is the parent company, which is a subsidiary company. It's very difficult to find. You will find a lot of other data sets, like probably the movie data sets, actors data sets, there's massive RDF which is sitting outside in the web. But it's very difficult to find data sets available for your research. It could be for your company, for your individual research. So this data set, what I'm showing right now, is completely open source. Meaning you can just go and download each of these data sets, and they're updated every week. So we are talking about massive data sets here. This data set is about 4 million companies' information, 4 million companies, and these are all, this is not just public companies, there's a massive chunk of private companies sitting here. People, which like today, if the only possible way of understanding who works in a company probably is LinkedIn, or some kind of mechanism where you find out who works in which company. But that person can work in multiple companies, he can be a director in multiple companies, and so on and so forth. So that single point of contact for various kinds of such information is not available today. But we have made it available. So this is, again, it's all open source. You can just download this data set, and you have access to 4 to 5 million kind of profiles, people profiles. So everything, by the way, is not in a CSV, it's not in a Excel format, it's in RDF format, which means it's open source, it's linked data format. You can use it in any database, graph database that you want. So that's the first thing that I want to emphasize. In the context of this talk, I want to just specify one data set, which is supply chain. That's what we have used to earn money, to be honest with you. So this is good, open data is good, but how do you show value to customers? How do you make the customers feel that there is value in this? So this is one data set which I want to emphasize. This is basically supply chain data set. Again, we don't employ people to figure out who is supplier, who is buyer. It's a machine learning algorithm. What we do is we run this machine learning algorithm through news, filings, and many other articles. So what this algorithm does is it figures out whether there is a buyer-supplier relationship in this piece of article. So this is what we have done. We have essentially, so there are other competing vendors outside, the competing people outside who actually do process this kind of information, but they do it in a kind of manual way. We have the scale. So this data set has allowed us to actually show whether there's a value in supply chain analytics or not. So just to emphasize, this is a completely machine learning algorithm output of our news. So we essentially run this algo on the news. Now what do we do in these? What does a machine learning algorithm do as such? So in our terminology, we call it a snippet. Any paragraph, wherever it appears, be it a news item, be it a filings, the algorithm runs through that snippet. It figures out if there is a supplier or a buyer mentioned in that specific snippet. And for each and every snippet, it comes up with the confidence score, whether there is a buyer or supplier. And then it aggregates the entire snippet of information into one specific supply chain agreement. So just to make it simpler, imagine there are 100 articles, and each of the 100 articles have, let's say, 10 paragraphs. So for each of the paragraphs in the 100 articles, it's going to come up with one buyer supplier, if at all it's mentioned, and then combine it to one buyer supplier across all these documents. So that's what I meant by combining this data. Now what I'm going to do is I'm going to show you a couple of things what we have done in terms of this, especially supply chain analytics. So firstly, I want to show something about as I said, about the open data. This is a data conference. So I just want to highlight for a few seconds this data set, this site called PermID is available to anybody, and all you have to do is you have to register, and you get, if you look at this, you can download essentially entire data set about organizations, instruments, codes, feeds, people, industry. Everything is available for free. You just can download and you can import it into any database that you want. Now, one of the most important challenges that we face, or in fact, most of you, if you're looking at combining data, is identifier. As an organization, we find it difficult if Tim Baker in XYZ database is he the same Tim Baker in another database. So that's the biggest problem, disambiguation of entities. So this was not a commercially, even though this is available publicly, this was not something which suddenly somebody thought of it and thought it was a brilliant idea. No, it was not a brilliant idea at all. It was something which we came up with to solve our internal problem. When I say we, Reuters has so many databases, and if a company in one database has to represent, or at least if you have to disambiguate that company across multiple databases, we need to have an identifier. So that's what we call it as perm ID. So for example, if I just type StarHub, so we have, let's say, StarHub Limited. We call this as perm ID, what you see as URI. This is a perm ID, which means if you can reference this in your graph, you call a node as with this perm ID, you can essentially connect everything. So that's the simple thing that I want to put it across. This is available for free. You can just try it out. Just to show how powerful it is, I've imported all the public available data into Neo4j, and this is probably a 2 or 3 days of effort. That's it. You can import all the entire relationship between organizations, people, industry, codes, everything into Neo4j, and you can basically do the analysis. What I'm going to talk right now is not something which we have done in the open source area, but we have done it with a bank. So this is an application which we developed for a transactional banking client. So the key idea is this. If I have to give a 1-minute summary of this problem or this application that we developed, for which we actually got paid, that's the reason why I want to emphasize this, that this is a practical application which the client saw value in it. So the situation is this. Transaction banking, as you know, they have their own internal data about who is the prospect, who is the customer. For example, if I am a bank, if Eric is my customer, Eric says transfer $1 million to A. I know everything about Eric, but I don't know anything about A. A is potentially a prospect for me. I'm a bank. Eric is saying transfer $1 million to B. In my database, I have nothing. I have no information about B except the name and probably the address. So our intention was to look at a graph that is resident in a company, in a transactional banking division, and then overlay, let's say, all this, whatever I'm talking about, open data, supply chain data. How does a graph which is completely devoid of external data, how does it look like if we add, or if we let's say overlay external data? That's the objective. And throughout our product or throughout our offering, we wanted to show the client, or if we want to validate ourselves, if there is value in it. If you take an internal graph and you overlay an external data, does it make sense? Does it add value? So that's what our project was all about. So I'll take about 30 seconds to just explain what is this graph that you're seeing. So this interface is basically a D3 interface. I just want to talk about the kind of graph what you're seeing. What are these bubbles? What are these graphs? What are these circles that you're seeing? These circles are the supply chain relationships between a customer of a bank. A customer of a bank is somewhere here, bigger circle. And all these circles that you're seeing are essentially either customers of the bank or prospects. So what you see as blue circles are essentially customers of my own banks. If I'm a bank, I know that this guy is a big customer, but he's transferring money amongst my own customers. So I'm not that interested about these guys. But all these green circles are all counterparties. I have no clue who they are. I only know their name, address, and so on and so forth. So all these green circles are potential prospects for a bank. When I say bank, I know this transaction happening. I need to know more data. Now, this information is already there. In terms of, in a bank, they already have this information, that this guy is a customer, this guy is a prospect. But where does RDF come in? Where does open data come in? Where does graph analytics come in? What we have done is we have essentially looked at this entire spectrum. of every big anchor. So every company, every transaction banking has such big customers. We looked at these big customers and studied their networks. And then what we did was, okay, can external data make sense? Can external data add value? Is what we wanted to figure out. So we developed this kind of an application. This is a fairly elementary screenshot of the application that I'm showing. It was far more advanced than this. So what we did was we came up with a way to represent. Now representing or showing value to somebody is as difficult as finding value. Sometimes you do find value, but you can't communicate the value sometimes. So in this case, what we have done in this simple visual is that we said anywhere wherever there is an orange line, orange edge, that edge is coming from external data. Wherever you see a blue edge, that's coming internally within the bank. So you can clearly see in a minute how many of your links are coming from your database, how many of your links are coming from external database. That's a quick, a business guy doesn't have time to look at all this. He doesn't even want to see whatever you are talking about. He says, how much of data that you are giving me in terms of graph. So quickly you can say, okay, these are the links that you have in your database. These are the links that we are providing. So that's kind of a quick summary, helps you to communicate value of this offering. We also give some kind of a metric and so on and so forth. So the second question from a complete business perspective is, okay, now you're showing all this fancy graphs. What do I do with this? So that's where we need to actually figure out how we do clustering of this algorithm. The people in the crowd might not, when we pitch these kind of products, 90% of the people don't understand what clustering is. They don't even care about clustering. What they want is how can I see value in this? That's a basic kind of audience that we deal with. In fact, most of you deal with, I guess. So what we did was for this entire network, we came up. We obviously there's fancy algorithms that one of those which Eric mentioned. We came up with algorithms to figure out what are the clusters in this entire network. So you see for each of these clusters, you see who are the counterparties in this cluster. Everything is a prospect here, by the way. So this is the prospect cluster, which has about 1,400 prospects. This is the prospect cluster, which has 400 members. So each of these, they can slice and dice and see whether it makes sense to target this entire cluster at once. So that's the idea of this entire analysis. And again, how do you target these hubs, whether it makes sense to target these hubs, that's a business decision which they have to take. When I say they, the business people. But as a data scientist, as a open data provider, as a analytics provider, all we can do is we can say, look, this is the hub. These are the main hubs that are present in the network, and it is up to you to make sense out of it. So this is a massive product we did, and it was fairly successful. And this is one application which we wanted to share with you. I don't want to take much of your time, but these are the two applications these are the 2 points which I want to reiterate. One is a free data. There's a lot of free data available, and which we have made it available per MIDI. Second is this kind of applications where you can overlay external and internal data, and you can see value in it. Happy to take any questions, either to Eric or me. Yeah.
So as the number of nodes increase, and looking at specifically in a big data scenario, concentrated in the graph database, you have so many of these nodes and points. So any suggestions when you're dealing with large volume of data that you want to present?
See, absolutely. See, I'll just show one specific example just to illustrate what you're saying. So in this graph, this is a mess. I mean, even if you look at, let's say, even if you look at a simple open source data set that is available, this is an organization. If I just click on this organization, the amount of links it will throw up is gigantic. It's a noise. Even though it looks simple, like, okay, take the data and do whatever you want, but it's so difficult. So what we typically do is we come up with metrics like centrality metrics, which can help prune the graph. So whatever you're seeing towards the left-hand side, all these are kind of more business filters, like you can filter based on country, based on sector. But what in a way, what this clustering is doing, it's kind of cutting out the noise. If you're saying out of these massive nodes, you concentrate on these 100 nodes where the flow is. So you're kind of, this is where probably machine learning and all these algorithms come in. So one of the ways is to use algorithms.
Again, thanks. It goes back to what we mentioned about 3Cs. You want to identify teams, clusters, subgraphs in this massive chunk of graph. Thanks.
Any more questions, please? Thank you. Thank you for the time.
Thank you.